The viewer who has followed my videos on abstract algebra has noticed, of course, that for most of them, I have tried to use notation, which is as general and abstract as possible. Only in the latest video of Lesson 6, I adopted the standard convention encountered in almost all textbooks. That is, in Lesson 6, I used the plus symbol for all additive operations and the dot symbol for all multiplicative operations. My rationale has been simple. Although the general notation makes everything look more complicated, I wanted my viewers to get the essence of abstract algebra. In general, a binary operation introduces an abstract relation between abstract elements of an abstract set. Although the definitions of algebraic structures are motivated by our experience, they're not referring to any familiar objects. In other words, abstract algebra is like Plato's world of ideas, a world of perfection which humans have no experience of. When humans use ideas from the Platonic world in real life, they use imitations of the ideas within the physical world. Similarly, abstract algebra is a world of ideas. In the abstract form, this world is not accessible to us. However, when we apply abstract algebra, we use imitations of the abstract concepts using familiar objects within our physical world. In math terminology, these imitations are known as realizations. My goal in this video is to explain how the imitations are created. Let E, star and G, circle be algebraic structures with one binary operation. A homomorphism from E onto G is a function f with domain E and codomain G such that the composition of two elements in E is mapped to the composition of the elements' images in G. If the function f is surjective, the homomorphism is called epimorphism. If the function f is injective, the homomorphism is called monomorphism. If the function f is bijective, the homomorphism is called isomorphism. If the domain and codomain of f coincide, the homomorphism is called endomorphism. A bijective endomorphism is called automorphism. The definition can be transferred to algebraic structures with two binary operations. In this case, both the additive and multiplicative structures obey the homomorphism requirement. Finally, the definition can be transferred to algebraic structures over a ring or field K. In this case, there is an additional condition for the scalar multiplications. Epimorphisms preserve many algebraic properties. Let F be an epimorphism from E, star onto G, circle. If the star operation is associative, then the circle operation is also associative. If the star operation is commutative, then the circle operation is also commutative. The neutral element of the star operation is mapped to the neutral element of the circle operation. If x prime is an inverse of x for the star operation, then its image is an inverse element of the image of x for the circle operation. Then we have the following immediate corollary. If f is an epimorphism from a semigroup, monoid, or group onto another algebraic structure, then the target structure is also a semigroup, monoid, or group respectively. Moreover, if the first structure is commutative, so is the target structure. Not all algebraic properties are preserved by epimorphisms. Indeed, the image of a cancelable element under an epimorphism need not be cancelable. For example, consider the set of integers endowed with addition and the set Z4 with elements 0, 1, 2, and 3 endowed with multiplication modulo 4. The function from Z to Z4, which maps any integer into the remainder of the division of n by 4, is an epimorphism. The number 2 is cancelable in the set of integers, but its image, which is also the number 2 in Z4, is not cancelable in Z4. If there exists an isomorphism from one algebraic structure onto another, we say that they are isomorphic algebraic structures. The structures possess exactly the same algebraic properties. One may derive the properties of one structure from those of the other mechanically by use of the isomorphism. Let 2z be the set of even integers. Then, endowed with the operation of addition, 2z is a group, and it is isomorphic to the group of integers endowed with addition. An isomorphism is given by the function f, which maps an integer to its double. Therefore, the two groups are identical. However, if we were to be asked if the set of even integers is identical to the set of integers, and the answer should be spontaneous, then our answer would be no. But why is this true? Our brains have been forced from very young age to equip any set with addition and multiplication. Hence, when no time is given to us to sort out what question is actually asked, the unconscious answer will be given with both operations assigned to the sets. The set of even integers endowed with addition and multiplication and the set of integers equipped with addition and multiplication are not isomorphic structures. More precisely, the set of integers with multiplication is a monoid, but the set of even integers with multiplication is a semigroup. The latter is missing the unit element. Hence, the two structures when addition and multiplication are taken into account are different. An additional important comment is in order here. The isomorphism between two structures must be for the entire structures. Otherwise, it is possible that all substructures to be isomorphic without the total structures to be isomorphic. Let's see an example. In the set of real numbers, we define the two operations star and circle between two real numbers to be the maximum and minimum number respectively. Then we consider the following two structures are endowed with star and multiplication of numbers and are endowed with circle and multiplication of numbers. It is evident that our comma star is isomorphic to our comma circle, of course, and are endowed with multiplication is automorphic. However, the two structures with the two operations defined above are not isomorphic. Let's prove this using the method of contradiction. Say that there was a bijective function f between the two structures. Using the multiplication, f must obey the following equation. For a positive number x, replacing x and y by the square root of x, we see that the image of x is non-negative. Also, setting y equals 0 gives that either the image of 0 vanishes or the function is constant. However, f being a bijection, it cannot have a constant value. Hence, it must be that the image of 0 is 0. Combining with the previous result, the image of a positive number must be positive. Using the star and circle operations, f must also obey the equation. For a positive number x and a vanishing y, this gives that all positive numbers are mapped to 0, which contradicts the previous result. Therefore, our assumption that there is an isomorphism is wrong. Homomorphisms and isomorphisms allow us to probe a structure by using the relations of a different structure. Imagine that the structure we want to probe is the abstract structure. We build a map to a familiar structure made of familiar objects, and this gives us a way to understand the abstract relations among the abstract elements. Such a map is called a realization. The familiar objects could be functions, could be number systems, could be matrices, and so on. There could be many different realizations of the same abstract structure. A realization, which is an isomorphism, is called faithful. Otherwise, it is called unfaithful. A faithful representation preserves and mirrors precisely all relations of the entire abstract structure. The most common realizations are through matrices. Since they are extremely useful, matrix realizations are given their own name. They are called representations. The abstract cyclic group is a group of n elements, all of which are powers of an abstract element G, known as the generator. In particular, if E is the identity element, then G to the n equals E. Although this definition is straightforward, being an abstract one, it does not provide the best way to fully appreciate its meaning. However, we can realize the group to get a deeper understanding of it. Clocks provide a realization of the cyclic groups. In this case, the generator is the unit on which the clock is based, and the operation is addition modulo n. Car wheels also provide another realization of the cyclic groups. In this case, the generator is the minimum angle of rotation, 2 pi over n, that leaves the wheel unchanged, and the operation is multiplication modulo n. To get a better understanding of realizations, let's select one of the cyclic groups, say Z4, and look at some of its realizations. The abstract Z4 group is isomorphic to the group formed by the set of the four numbers 1, I, -1, and -I, equipped with the operation of multiplication. In this case, The element I is the generator with the property I to the 4 equals 1. Then, consider the set F of the following 4 functions. We equip the set F with the operation of function composition. It is easy to verify that F becomes a group and it's isomorphic to Z4. The generator is the function G. As a third example, consider the set G of the following 2-dimensional matrices. The set G equipped with matrix multiplication is a group and it is isomorphic to Z4. In fact, it forms a representation of Z4. In particular, it's referred to as a 2-dimensional representation, exactly because 2-dimensional matrices have been used. In this case, the first matrix is the generator. For my curious viewer, I will make the following comment, which relates examples 1 and 3. Recall that when a complex number is multiplied by the square root of -1, this amounts to a rotation of the complex number by 90 degrees. Then, the first realization represents the rotations of the points of a plane by 0, 90, 180, 270, and 360 degrees when the points are written in complex notation. And since a number is in one-dimensional square matrix, we may see the realization as in one-dimensional representation of Z4. In example 3, the 2-dimensional representation of Z4, the matrix R rotates the points of a plane by 90 degrees when Cartesian coordinates are used. Hence, the third realization represents the rotations of the points of a plane by 0, 90, 180, 270, and 360 degrees when the points are written in Cartesian coordinates. All 3 realizations of the abstract cyclic group, Z4, which were given previously, are faithful. Now, let me show you a realization which is a homomorphism but not an isomorphism. We consider the set of the 2 numbers 1 and -1 equipped with multiplication. This creates a faithful realization of the abstract Z2 group. Now, we map the abstract Z4 group to the realized Z2 group, such that the generator G of Z4 is mapped to -1. This function captures some characteristics of the Z4 group, but it does not reveal all relations. It is an unfaithful realization. I will finish my video with the following comments. There is an entire area of mathematics known as representation theory, which studies all possible realizations and representations for each group. Our universe is a realization of the Poincare group. The elements of this group are the 4-dimensional translations and rotations of space and time. Although I will not say anything more on this at the moment, I hope that just the statement itself excites and motivates you to study more algebra and mathematical physics. And with this comment, I have finished my presentation. I hope you liked it. If you did, please subscribe to my channel to help the creation of more videos. Thanks a lot for your support.